All right, so this will be a quick, just jotting down some independence, quick example in the U try, and then I think we're done here. So to prove independence in IB, you want to use a couple of different ways to do it. One is to show that a conditional probability is exactly the same as the probability without the condition. That would be something like the probability of A happening given B basically is the exact same as probability of A happening with no reference to B at all. That means the probability of B happening had no impact on A, therefore the events are independent from each other. And this is just the probability of A happening given that B didn't happen. And so those would all have to be the same, meaning that B happening or not had no impact or influence on the probability of A. So if we were talking about flipping a coin, like heads, and this would be the same as tails, which is not heads. This is heads, this is tails or not heads. And make a tree diagram like we did before, and come down here and talk about the intersection of A happening and B happening would be, in essence, multiplying two events in a row that happened. And again, if that is the same as this, which is our formula from when I did the little algebra of the last video from our conditional probability. So if A and B are independent of each other, then this probability right here is actually equal to the probability of A. We just talked about that up here. If two events are independent, then B doesn't impact the probability of A happening. So knowing this formula from manipulating our conditional formula, if these two events are independent, then this guy up here just equals the probability of A. And so if events are independent, the intersection is the product of the two. So this means and so I've said this before in the videos as well. When you see the and means multiply. And so if I've got an and in here, I'm allowed to multiply, boom. And you've been doing this all along with your tree diagrams, because you just multiply along your branches. So this is the first event, this is the second event, and if they're independent from each other, which for us was when we replaced the item back into it, then this probability wasn't changed by this and you still multiplied them. If they were dependent on each other in some way, so we didn't replace the item, we kept the card or the marble, it changed the next probability, and we already had taken that into account based on what happened here. And so that's this situation, and you were still multiplying them. So the end of each of these trees is just an intersection, is the probability of getting a heads and another head. And notice that that is this symbol, and we've been multiplying along our branches. So that hasn't changed at all, but if they tell you things are independent, you're allowed to multiply the two individual probabilities together. And this can also be used to show that events are independent. If you know this intersection probability and you know the individual ones and they're equal or very, very close to being equal, you can use that as a verification that indeed events appear to be independent. So a quick example as promised, and then you will be able to do one as well. And I think this probably is actually supposed to say example 7 according to the worksheet, so I'm just going to quickly change that. All right. Probability of A is a half, probability of B is a third, and I don't know what the probability of the union of A and B happens to be, and that's what I'm asked to find. This is asking you to find the probability of A or B. And again, A or B means I can add the two probabilities together, or means add. And I just have to subtract whatever their overlap is, which happens to be their intersection. So I'm supposed to find this P if the two events are mutually exclusive. Well, if they're mutually exclusive, then there's A and there's B, and there's no overlap. So if I want to find this, I can actually just take the probability of A plus the probability of B, which is a half plus a third. And if I add those up, I'll get my answer for part A. And I would have to get a common denominator, which would be 6. So this is 3/6 plus 2/6. So this answer would be 5/6. So A or B, if they're mutually exclusive, would be 5/6. Now I want to find the same thing if A and B are independent. So if I tell you two events are independent, what you automatically know is that the intersection of A and B is the product of A and B. because and means multiply. And if they're independent, I know this is true. I don't have to worry about the conditional piece here before I multiply. So now, if I want to find the union, remember the union, and again, this is a separate question, so it is not implying that this is still the case. I would take the probability of A plus the probability of B, this is our formula from earlier video, and subtract that intersection because otherwise this is being counted in both of these. And now I can figure out what this is. Again, that's just me calling this P. I can go 1/2 plus 1/3, but they aren't mutually exclusive anymore, they're independent. So I can also take away this intersection, which is the product of 1/2 times 1/3. So this is me doing the little calculation up here. I'm allowed to multiply those only because they're independent. Kind of yelled at you. So I already did some common denominators with these two guys. So I already know that these two add up to 5/6 because I just did it right here. So that's kind of a little bit of a cheat on my part. Minus, I multiply 1/2 and 1/3, I get 1/6. So this answer is 4/6 or 2/3. So there's a little bit of this key word right here leads me to this special separate formula that I can calculate and then substitute right there and do the subtraction. And only because they're independent. All right, you're going to try it. Wow, you got a lot more questions than me. Sorry about that. You've got probability of X, probability of Y, and X and Y are independent, so that's big information. And I want you to determine the probability of all of these things happening. So pause the video and give it a go. Okay, here are your answers for each one of them. And if you needed to kind of figure out a little Venn diagram for this, which may have helped with some of these, you could have had X and Y, and because they're independent, I know this little overlap in here, which is X and Y, that's X and Y. I know that I can get that by multiplying these two. So if I multiply those two together, I would get 0.35. And again, all of X has to add up to 0.50. So all of X means I now know this has to be 0.15 because this X circle would add up to 0.5. All of this has to add up to 0.7. So this side of the Y would have to be 0.35. And then you could add all these up. That's 70, 85. That means I know that there's, to make a full 100%, this would have to be 0.15. And that's how you can get some of these answers. Both X and Y is this overlap. You get that and means multiply. They're independent. I don't have to worry about conditions. So you multiply those. X or Y or both. That's basically asking you the union of those two things right there, which means I can add this to this, but I have to take away their intersection, which I just found. So if you add those and then take away the intersection, you'd get 0.85. If you forgot to take away that intersection, you'd have more than one. You can't have a probability more than one, so you know you had a problem. Neither X nor Y, that's out here. X but not Y, that's just this piece. This is X, but not including that, which is also Y. And X given that Y occurs. So here's my condition, which means my denominator has to be Y. So my denominator has to be everything that's in Y, which is 0.70, which I already know from right here. And I just want the X portion of it that happens to occur in this Y circle. And again, that's the this top part is the intersection of X and Y. And that means I could multiply. If you hadn't already done it, that would be 0.35. And 0.35 and 0.70, I don't care about the decimals. 35 over 70 is a half, which is 0.5. All right, there you go. I explained a lot of that. I think that's it. Again, probably on your note sheet, this is you try 7. And look, no more. That's the end. So enjoy. Sorry there was so much video today. Just engaging video.